Look up at the night sky, and you're seeing the universe on its most massive scale. To understand how it exists, we must fall inward, past the cellular level, past the molecular bonds, down to the core of a single atom. For a long time, our best map of this microscopic world came from the Danish physicist Niels Bohr. Looking at this diagram of his model, the atom is elegant and easy to visualize. A dense central nucleus sits in the middle, while negatively charged electrons circle around it in fixed, perfectly circular orbits, much like planets orbiting a star. It was a concept that helped us grasp the basics of atomic structure. But as our tools for observing the microscopic world improved, we realized this planetary system was an illusion. The true nature of matter is far stranger. The first cracks in the model appeared when scientists looked closely at the light emitted by hydrogen. Instead of simple, single emissions, high-resolution spectroscopes revealed groups of incredibly fine lines. Bohr's single-track orbits simply couldn't account for this complex splitting. There was also a physical limit to what we could observe. To locate an electron, you have to bounce a photon of light off it. But because electrons are so small, the energy of that light disturbs the electron's exact motion. You can know where an electron is or how fast it's moving, but it is physically impossible to measure both at exactly the same time. To find the source of these contradictions, Max Planck proposed that electromagnetic energy isn't a continuous wave. Instead, it travels in discrete, indivisible packets. Planck's equation, E equals h nu, shows a quantum's energy corresponds to a specific frequency of light. When an electron jumps, then snaps back to ground state, it releases that exact packet as a flash of colored light. Every visible color you see in a rainbow is the result of these microscopic quantum jumps. The exact wavelength determines the color, from a long red wave down to a short violet one. Because electrons absorb and emit energy in these sudden, discrete steps rather than smooth paths, they don't follow defined tracks. The atom doesn't have a rigid boundary. Physics needed a completely new way to map it. That new map came from Erwin Schrödinger, who developed the quantum mechanical model of the atom. Instead of hard orbits, Schrödinger realized electrons exist in orbitals, three-dimensional clouds where an electron is most likely to be found at any given moment. To define the location and energy of these shifting clouds, physicists use a set of mathematical coordinates called quantum numbers. The principal quantum number, n, dictates orbital size, expanding shells outward. The angular momentum quantum number, L, determines shape, like spheres or dual-lobe dumbbells. Finally, the magnetic quantum number orients these shapes along the x, y, or z axis. Together, these three numbers provide the 3D blueprint for the atom, carving out the exact regions of space where an electron is allowed to exist. There is a fourth and final property, spin. Electrons have an intrinsic property of spinning on their own axes. They can only spin in one of two opposite directions, clockwise or counterclockwise. An atom might have dozens of electrons. If they all crowded into the lowest energy space, the atom would collapse. So how do they populate these orbitals without causing chaos? Electrons follow strict occupancy rules. First, the Aufbau Principle dictates filling the lowest energy levels. Second, the Pauli Exclusion Principle allows only 2 electrons per orbital, requiring opposite, anti-parallel spins. Finally, under Hund's rule, electrons occupy equal energy slots singly first before pairing up. These 3 rigid rules organize the electrons perfectly. They create a stable, structured hierarchy out of what would otherwise be total quantum chaos. When you apply all these rules, the modern model of the atom emerges. It is a dense, overlapping web of spherical and dumbbell probability clouds pulsing in the microscopic void. The exact arrangement of these electrons determines the behavior of every element on the periodic table. It is the extreme outer boundaries of these probability clouds that interact. The shape and occupancy of these outermost orbitals dictate exactly how atoms bond together to build the molecules of our physical world. Those molecular bonds build the chemical reactions in our cells, the materials of our planet, and the stars in the night sky. From the movement of an electron to the structure of a galaxy, the universe is built on these invisible patterns. Every physical object is the final result of how these smallest parts are organized.